Recording. What's wrong? What's wrong with the? Oh, you want me to open the window because it's like hot?
Yes. Oh, wait. Does your thing blow out cold air ever?
I doubt it.
You got it
With the wolf.
I meant that. That thing.
All right, 20. We got y equals 5 minus x, and y equals 0, and y equals, is it 4? And x equals 0, and then we want to revolve this about the line x equals 5. So rotate. Revolving and rotating are the same thing. Rotate about x equals 5. So 5 minus x has a y-intercept of 5 and then a slope of -1, so you're going down. Y equals 4 is just a flat line there. Y equals 0 is a vertical, what the hell is wrong with me? It's like this. Yeah, probably. And then x equals 0. So we've got 1, 2, 3, 4, 5. And then we're going to rotate about this vertical line.
It's a little squishy.
Yeah, it's not the straightest line I've drawn ever. Sorry. I'll fix it for you here. I'm sorry. So you have y equals 4, y equals 0, diagonal line, x equals 0. So we've taken between y equals 4 and y equals 0. So we're not using this little triangle up top. So you can get rid of this little triangle up top. That's not going to be part of the region because it's above the y equals 4. So we take this thing and then we rotate it about this line x equals 5. So we're doing things in terms of what? X or y? Y, because we're rotating about a vertical axis, which means I need to go to my line equation and rearrange this. So this is going to be x equals 5 minus y. And then we got to figure out big R and little r. So little r is the distance from the axis of rotation to the closer edge of the enclosed space. So that's a little r. So little r is going to be what? 5 minus y. And that's going to end up being y. Oh, that works out very nicely. And then big R is the distance from the axis of rotation out to the far edge of the enclosed space. And that far edge is just this straight vertical line. And so that distance is always 5. So big R is 5, right? And so we can put these things together and say our volume formula is going to be pi times the integral from who to what? 0 to 4, because we're going up the y-axis. And then big R squared is that not? Okay. Big R squared is 25, and little r squared is y squared. And so you have 5 squared minus y squared looks like that, and you're on your way. So, so 5 squared minus y squared. At this point, I think you'd probably be fine, because as far as integrals go, this is one of the easier ones you have to then evaluate. Is there anything else we wanted to look at from the homework? Or is it just number 20? I remember last year what threw me off was this like extra little triangle up at the top, and I wanted to include that.
22, Diana.
And I needed not to. So 22 for Diana? All right. So
and I was going to ask, so even if it's a horizontal line of no axis of rotation, so the little r would be the one right below the line. Say it was a horizontal, say it was like y equals 4 or something, instead of like
so if we wanted to, so you're saying if we wanted to rotate about a horizontal axis, you mean?
Yeah.
So,
little big R will be the one furthest away.
Yeah, so big R will always be the distance to the farther away edge. So if we rotated around like y equals 6, little r, this would be tougher. Little r would be, say, 2 for this first little section from 0 to 1. And then it would be 6 minus x, or 6 minus 5 minus x for the second section here. So if we were rotating this about a horizontal axis, we would end up with two integrals. One integral from 0 to 1, where the top edge is flat, and then a second interval from 1 to 5, where the top edge of the region is diagonal. And so we'd have little r is 2, and then little r is 6 minus the diagonal line. And then all the way across, big R would be from 6 down to the x-axis, and that would just be big R is always 6. So the little r is always the distance from the axis of rotation to the inside edge, or the edge that's closer to the axis. And then big R is always the distance from the axis of rotation to the farther away edge. And then you just got to pay attention and see, is that going to change at some point along the way, like it would here if you rotated about a horizontal axis. Does that answer your question, Diana?
It's Diane, but yeah, and
Okay,
then
sorry.
always big R minus little r, right?
Yeah, and then it'd still be big R squared minus little r squared in the integral.
Okay,
All
thank
right.
you.
And then, did somebody want 22? Yeah. Okay. So over here, let's look at number 22. So we got.
Says you. You be blocking the whole
I know, like
You're blocking the whole
take your hat off and like put it
And
next
what's
to
this
it.
today?
22. Oh, now he sounds all self-conscious and has to. My goodness.
Well, remember in the beginning of the year we used to go warm up, and then both their big heads would block the warm up every
You
year.
and then you times two, which made it worse.
Yeah.
No one had no idea you were blocking.
Yeah, because no one has no idea what's going on ever.
It's turned back into pick on the whole time. Sorry. I tried.
No, I love you.
Lies.
Don't cry.
All right, and so we're gonna. This is also our axis of rotation. So that's our equations. So we're rotating about a vertical axis again. So you got 1, 2, 3, 4, 5, and that's also the edge of the interval. So hopefully this is just going to be a disk then. And then we have y equals 2 and y equals 5. And then probably we want to do this in terms of y. So we'll have x equals 5 over y, because we're rotating about a vertical axis, so we're going to have to do stuff in terms of y. So if we start with y equals 2, 5 divided by 2 is x is 2.5. And then 5 divided by 5 is x equals 1. So if you plug in the y equals 2 and y equals 5, that kind of gives you points on the x, y equals 5 curve. And you can draw that. And then it's this region here. So we don't need this stuff out here, because we want to be in between y equals 2 and y equals 5 and this curve and the line x equals 5. So that's the region, and then we're going to rotate it about this line, x equals 5. Any questions with setting that up? Just the picture and making sense of that. So once we've got that, coming up with the integral, we got to think through radius. Do we have a big R versus little r here? No. So what method is this? This is a straight disc, so not washers, just plain old discs. And the our radius is going to be from the edge of this curve to the axis of rotation. That's your radius. Radius is going to be what? 5 minus 5 over y. So the axis of rotation 5 minus the curve 5 over y. So once you got that, put this together in your volume formula. Volume equals pi times the integral from 2 to 5 because you're going up the y-axis. And then r squared is 5 minus 5 over y squared, and then dy. If we tried to clean this up before integrating, what would this be? You could, but then it's going to get squared and be 25. Because this is all squared.
Oh.
So if you pull out a 5, that's fine. Just be careful when you pull that out, you square it. But right now we're trying to square this whole thing anyway. So what's 5 squared? 25, and then minus 50 over y, because you have 5 times this, and that happens twice. And then plus 25 over y squared. And then when you integrate, that one's easy. 25y. This one becomes 50 ln of y. And then this one becomes, 25y to the negative first, or 25 over y. And because it's y to the negative first, when you divide by the new exponent, this becomes a minus. So this could be a little tricky with the integration of, hey, we have a natural log in our integral, and then this thing is not a natural log. This is, think of this as 25y to the negative 2, and then backwards power rule, but with the negative exponent. And then from here on, moderately annoying, but it's not the worst thing ever. Diana, do you need anything, or Diane, I'm sorry, I don't know which of you asked for this. Diana, so do you need any more with this, or does this make sense now at this point?
Yeah, it makes sense now. Thank you.
Anything else for the homework? The last homework on washers and or discs. I think.
So yesterday, like below it, you said there was like a practice packet that came from
Yes,
class.
I forgot.
Oh, okay.
So here that is.
I was like,
So,
I don't remember getting a practice packet.
I've posted this practice packet on Schoology for those of you that are virtual, and for those of you who are like live. Here are copies of this. This is not so much for washes and discs. This is for just going back to 7.1. And there's a lot here. So there's a whole ton of textbook problems that we haven't touched yet. So if you want more practice with washes and discs,
What did I say wrong?
if you wanted more practice with washes and discs, if you go into the textbook, and there's several problems that we skip, like we didn't do 12 or 14, or several of these, 23 and 24, and so on, through 30. So there's a bunch that we haven't done with washes and discs that you could do out of the textbook, and then this thing is for areas between curves from 7.1.
Pretty sure kidneys are doing what you thought.
Oh, you like the kidney?
Well, the problem just says the kidney shape swimming pool.
Yeah.
So now we're talking about kidney shape.
Like, why wouldn't you make a swimming pool in the shape of a kidney?
Well, no, I'm saying I think like the kidneys are different shapes depending on whether it's the right side of your body or the left side of your body, so it has to fit.
They're not just mirror images?
I don't know.
How about for lungs? Is that the same? Lungs are the same?
Lungs are the same. Yeah.
So I haven't like done a lot of cutting people open recently. So.
Sorry.
Recently.
Yeah.
Before I was a teacher.
I know, it's exactly right.
All right, so you know what? I can get just as much fun tormenting people with math. So,
Why don't you just ask me to move it on? Like, or I'll look it up in my head or something.
so what's up?
He's complaining about my head.
Whatever.
We've been in here for
He can
years.
move. So we're going to move on to finding volumes of regions using cross sections. So this is the same idea in that we're finding volumes and we're taking a two-dimensional shape and turning it into a three-dimensional idea, but not with rotation. So up till now, with this 3D stuff, we've always been, you draw a curve, and then you imagine rotating that curve around some axis so that you're kind of generating some sort of circular motion. And so we basically always have cylinders involved, and that's where we always have like pi r squared, basically. Thank you. With this stuff, instead, we're going to take a curve. We'll come back to this thing. Take a curve, so maybe you can't see the curve very well, but we have two curves here enclosing some region. And then what we do is instead of rotating that region about some axis, we say, what if coming out of the curve at us, we have semicircles? Ta-da! Or squares. Can't see it?
Online, it's better if you,
You should just draw the curve and then talk about it.
How about this thing? So I'll leave this here. Drew. Just hold it out. Thank you. And
And they're all the same. You can kind of see it.
yeah.
You can see this.
But the
You just can't see
semicircles,
that curve.
they don't have the same region. Yeah,
That's all.
Exactly.
Oh, that's why I wanted to.
Of course it confuses.
Oh, okay.
So we've got some enclosed region on a graph. So
Camera?
yeah. Nice. And then so we've got the enclosed region here. Boom, boom, boom. Boom, boom, boom. And then we're not going to take this region and rotate it about some axis and make a bunch of like rings. What we're instead going to do is say, what if on this graph we have semicircles growing out of the graph at us, perpendicular to the xy plane? So you can imagine this is the base of the semicircle, and then the semicircle is coming out like this. And then we have another semicircle right here coming out like this, and so on and so forth. Or it doesn't have to be semicircles. They could be squares, or they could be triangles. And so you end up with like a point here, and then it's sloping down to the edge. But you have some sort of cross-section coming out, whether it's semicircles, or triangles, or rectangles, or squares, and they're all the same, and they're all coming out towards you. And you end up with, and if you're at home, this isn't going to do much for you, but you end up with this, where in this case, coming at you are a bunch of squares. You can kind of turn on its side of the square, and I can knock this down. One behind is another square, behind it's another square, and the squares change in terms of like how tall they are, and that's going to depend on how thick the curve is from top to bottom. So like here, the distance from top to bottom isn't as wide as it is up here. And so this square will be less tall coming out of the page at you than this square would be. And what we do is basically the same kind of Riemann sum, slice it up into a bunch of squares, or into a bunch of semicircles, or into a bunch of whatever the shape is. Find the areas of all these squares, and then integrate over the interval to turn that into a volume. Yes, ma'am.
So if it were triangles, what's the height? How would you determine like the different heights?
That's going to be determined usually by how far it is from top to bottom. And we'll get into like the particulars of these different shapes as we get into actual examples. What we first need to know is all of our formulas for the areas of these shapes. So we need to know, okay, well, what is the area formula for a square? And what is the area formula for a semicircle? What is the area formula for an isosceles right triangle when the base B is length?
So this has nothing to do with volume.
Oh, it still has to do with volume. But just like, you know how in our volume formula for this method, we have pi r squared. That's the area of a circle. And then we integrate over the width, and that's where we get the volume. It's going to be the same thing. We're going to have, forget pi now, area, and then integrate over an interval, and that makes a volume. Because that dx or dy differential gives us like the thickness of that. It's not a disk anymore of that slice. So you have with a square, base times height, That's the area of this square. And then he's got a little bit of thickness, infinitely small thickness. That's dx. And then we integrate over the dx. So base times height gives us area, and then dx gives us volume now, and then we integrate over all the dx's through the interval. I don't know, because you had to come up with like the equation yourself, and for the upper curve, then you have a lower curve, and that gets an equation. And then there's a whole bunch of work on the back to come up with. So Mr. Snow's former BC students.
Oh, so it's like a project.
This was like a post AP exam project.
Post AP exam.
I think so, yeah.
This is yeah, we
Luckily, he doesn't like projects.
You're in luck. You've seen my artistic abilities, and you've seen how I like run down
What
my
if we
daughter.
did a
for
giant
her.
one the whole time?
Yeah, we're not.
We could put it right there.
I would be more inclined to say like,
Team effort.
let's learn matrices, because that's something you should play before you graduate. And then after that, maybe play cards and talk about probabilities. That's a square.
Yeah, how do you know?
You go to a
How do you
field
know?
Something like that. The guy who was the AP Calc teacher before Snow, so not the guy who taught me, but the guy before him, he would just do pinochle tournaments after the AP exam.
Okay, well, go to a
Pinochle is a card game, so he would teach his students how to play pinochle, and then they would have tournaments.
Ooh, yeah. We play poker
We'll see.
instead.
No, because we're not wagering money on stuff.
Play math.
So this is a sort of thing. So keeping with our like garden and Eden thing, we have the snake, we have the fruit. So you have a curve here and a curve up above. So that's where we get this thing. So the upper edge of these apples is one curve, the lower edge of these apples is another curve. And then between the curves, you have, in this case, semicircles drawing out. You can see it a little better this way. And you find the area of the semicircles going across, and then you integrate over the interval. I know if you did, because I looked at it. Oh, in general, they'll tell you. So the problem will tell you, we're doing
I look at
this shape. So your homework, your first homework on this stuff is not due tonight, because we're not even going to get to an example today. So you know how like we took probably 2 or 3 days to just introduce disks, and same thing's going to happen right here. Could you kill the light, please? Let's get into these formulas.
I think we should go on.
I would love that, but
I thought we were allowed to.
then I'd have to like organize it.
I'll do it for you.
All right. So solids. So we just talked about it. You don't always generate the solid by rotating about some axis. Sometimes you have a flat plane, and then coming out of the plane, which is the graph, you have some two-dimensional shape. So we got to know the areas for these different shapes. What's your area formula for a square?
Length times width.
Nope, that's a rectangle.
Oh, S squared.
Thank you. Your side squared.
Wait, isn't it?
Technically,
Technically,
you
they're
could
the same
use
thing.
length.
You're gonna want to have the distinction. Rectangle is
Length width.
length times width. Semicircle is
1/4 pi squared. Isn't it just a half of
One half.
that's half a circle.
the circle? 1/2 pi.
A circle's
Is
not
circle
one
a half pi squared?
No.
I don't know.
A circle's
Pretty
not
sure it's a full pi squared.
Is it?
Yeah,
Are you sure?
yeah, pretty sure.
And what's the one?
I'm not a geometry teacher, but I'm pretty sure a semicircle is a half.
Alright, come on, however, it is half pi. There.
Oh,
There you go. That's what I'm getting at. All right.
This is why
And
I'm
then
older.
let's skip over these weird things for a second, and let's talk about how a trapezoid. Because triangles get weird.
One half.
The area for a trapezoid is
something base 1 base 2.
something base 1, base 2.
One half.
1/2.
1/2 base 1, base 2. Because
times
really,
base one.
you're just averaging the bases. And then height. So with the trapezoid, you got 2 bases, you average them. It's kind of the same as like a rectangle, 1/2 base height, except there's 2 bases instead of 1 base in a trapezoid versus a triangle. Now, these things. An isosceles right triangle with the base B as a leg. First of all, what? No.
Okay.
What is an isosceles triangle?
2 equal sides.
2 equal sides, and if it's a right triangle,
It's 90 degree
90-degree
angle?
angle, and base B is a leg. So if it's an isosceles triangle, instead of base times height, we would have base times base. And one of those sides that are the same is the leg. So the hypotenuse is not B. So this is the situation where if you imagine back to your graph, one of these legs is the thing that's sitting in the graph, and then it's coming up out of the graph, and the hypotenuse is coming out of the graph, and the other leg is coming up out of the graph. So in this scenario, your area is 1/2 B squared, because base times height is base times base, really.
Oh.
We like this scenario. This is the least painful scenario. So base B, that base is referring to the edge of the shape that's in the graph. And then everything comes else out. So like in the semicircle, the diameter lies along the graph of the, like between the two curves. In a square, that's pretty straightforward. In a rectangle, that's a little more complicated. You got to decide, is it the length or the width that's lying in the graph? Triangles, you have three options. You can have one leg lying in the graph, or the other leg, or the hypotenuse. Now, hopefully it's an isosceles triangle, and the two legs are the same, and that makes life a little easier. In this scenario, you have an isosceles right triangle again, but now the base, as in the side that's lying in the graph, is the hypotenuse. So this is going to be what that looks like. And this is your right angle up at the top. And so the area here is a lot more complicated. And about 11 months ago, I had that memorized, but I haven't taught this. Yeah, because
Can you guess what it is?
I taught this a year ago.
Can you guess what it is?
Yeah, you can guess.
It says the 1/2, right?
Oh, I can't read my own writing.
What are we guessing exactly?
The area formula for that thing, where the base B is the hypotenuse of this shape.
But the other two sides are still.
The other two sides are still equal, but you don't know what they are in terms of B. I mean, you could find them out in terms of B. You want to go ahead and derive it?
Well, 'cause if we have
If we had more time, I would.
Isn't there, like, you could just use the 90-30-30 triangle thing?
Yep.
And then you just have the two sides.
Yeah. It's B squared over 4, or 1/4 B squared. So it's actually not that complicated. That's 1/4 B squared. And you could come up with that if you said what Sam was saying. Like, this is a 45-45-90 triangle. So if you call these two things, say, like x, you could solve for x in terms of b and then do 1/2 this thing times this thing. All right, now the equilateral triangle is side B. Now with an equilateral triangle, that's the toughest situation because you don't just have like 1/2 base times height because you don't have a right angle in this thing. So here, all three sides are the same. Base B is lying in the plane, and in that scenario, you're going to end up with area is 3B squared over 4.
Are they
So B is going to be the distance between the curves
Yeah.
on the graph. So you'll be able to figure that out. B is going to be like an expression. Like over here, instead of R, like big R and little r, we'll have B now. And B will be an expression in terms of X. And then you plug that thing for B into one of these formulas for your area equation. So you might go back to square and say, you know, instead of side squared, we'll call that B squared. And instead of length times height, width, we might call rectangle base times height. And then semicircle is 1/2 pi r squared. And just remember, that's the radius. In one of these problems, the base is going to be the diameter, so the base is 2 times the radius. Or a semicircle sort of thing. So in all of these formulas, the base is the side that's lying in the plane, and then the shape is coming out of the plane at you. We'll get into like, okay, now we know our formulas. What do we do with them? And that'll be tomorrow as we get into like steps and formula for the actual volume that we're finding. So here it's tougher. We have like 2 levels of formula. We have the formula for each individual shape that is going to make the cross section, And then you have the formula for the volume formula of the cross section, of the shape of the solid that you're making. Nope. They'll give you the shape and they'll give you the area enclosed on the plane. So they'll give you this curve and they'll give you this curve, and they'll say, all right, in that enclosed region, coming out of the plane as cross sections are squares or whatever it is. Oh, I forgot to roll the dice, didn't I?
Yahtzee. I'm gonna wait till you get Yahtzee on your face.
All right, 2, 4, 5, and 3. So I'm collecting rows 1 and 6. So rows 1 and row 6. Please hand in your homework. 2, 3, 4, 5 is a small straight.
Yeah.
True story. All right. So,
I'm gonna start bringing in a Yahtzee sheet, and then I'm gonna fill out.
oh, also, for the examples that we do in class, I'm gonna have a packet for you guys to save with like having to write stuff down because they're all wordy. I'll get those out when we get to the examples. So this is 1 and 6, and this is
So you put stop.